So we are looking at thermal properties, thermal physics on a whole. All right, so these equations is just here to give you a little reflection on what you've learned from CSEC days. Anybody remember the use of these equations? Yes, who wants to tell me how we use any one of these equations? Why we use any one? Go on, nobody?
Yes, sir. One is to calculate the latent heat, or the heat required to change a substance state without changing its temperature.
All right, great.
And the
All right.
other one is the heat energy required to change a unit mass of a substance by 1 Kelvin or degree Celsius.
All right, great. Thanks very much. So the first two is to quantify the amount of heat required to change the state of a substance. So the LV1 is to change the state from a liquid to a gas, and the LF1 is to change the state from a solid to a liquid without the change of temperature. And then the third equation is to change the 1 kilogram object by 1 Kelvin in temperature. All right, so we're going to actually reflect on those equations as we move along in this aspect. All right, so what we're going to first look at is the concept of total internal energy. All right, so in terms of gases, not all molecules in a specific volume of gas at constant temperature has the same kinetic energy. Right? Because these objects or these particles of gases, they move with different velocities, so hence their kinetic energy will not be the same. Right? So in that case, to find the total internal energy, it's basically the sum of all individual kinetic energy and potential energy within the system or within the container that has that specific amount of gas. All right. Now, the question I would like to ask is, why do you think the gas molecules will not have the same kinetic energy? What would cause it not to have the same kinetic energy? And so let's take that on.
Sir, is it that some of the energy is used to break bonds? So the kinetic energy is converted to potential energy, and that energy is used to break any bonds or particles there to change state. So some particles may have kinetic and some has potential.
All right, so that answer would be if we're looking at the change of state, but we're just focusing on just gases. All right, so it's not changing state from being a gas, but what we're looking at is why the individual gas molecules. So example, if we have a container that's filled up with oxygen gas, right? Why does individual gas oxygen molecules have different kinetic energies? Why is it that all the molecules there have the same kinetic energy? Right? And we see here the main difference is the velocity, but why does the velocity change? All right, let's help you out. Velocity is a vector quantity. So if a quantity is vector quantity, what does that mean?
it as magnitude and direction.
Magnitude and direction. So the part that we're going to look at is the direction. What do you know about direction of motion of gases? Yes, anybody? What do you know about the direction that gases move?
In a straight line.
In a straight line, but alright, more than just straight line. What else? When they move in a straight line, what else in terms of direction? Think about the principle of Brownian motion. When you see the dust particles in the air when there is sunlight shining through. Alright, great. Somebody said all direction. Alright. So that is the answer. Gases move in all direction. Right? So we know that velocity is a vector quantity, and hence if it changes direction, then that means it changes the value, right, of the kinetic energy. But also not because it changes direction, but also we know of things that are called isotopes, right? So in reality, when we have a container that is of oxygen gas, it's highly impossible to have only oxygen that is just one type of the isotope, meaning oxygen has an atomic number of 12, right? So it's highly unlikely that all the molecules of the gas are actually of the oxygen 12 molecule. It could be that some will be oxygen 14 or some oxygen 13, but it's still oxygen gas. It's just that there are different isotopes. And if it changes the mass, then also it will also change the kinetic energy as well. Alright, so that's the reason why gases have different kinetic energy at the same temperature. Alright, now we're going to look at the heat flow in a one-dimensional aspect. Right, so this just means that if we have a metal, we're looking at the heat flow from one side of the metal to the next side. Right, now here is the equation that we should remember, that Q over T is equal to half Ka over Ka times delta T over dx. Right, so the K over T tells us it's the heat transfer per unit time, and we know that heat transfer per unit time is another quantity known as anybody? What term in physics is the heat transfer per unit time? Come on, guys, let's make this interactive. Anybody? All right, hint. What's in the bracket should give you a hint of what it is.
Potential energy.
Thermal energy.
Not thermal energy. Work? No, not work. Going close. What do you think the W in the bracket means? No, not joule. What do you think the W in the bracket means?
What?
Watt. So therefore, what is measured in watt?
Power.
Power, thank you. Alright, so power is measured in watt. So Q over T is basically the power of the heat transfer, right? So heat transfer per unit time is the same thing as power. All right. Now the K represents the thermal conductivity of the material, and what that is, it tells us how easy or how fast the material will actually transfer heat from one point to the next point. Right? So we know conductors are good, metals are good conductors, while plastics are poor conductors. So that means metal would have a higher conductivity than plastic because it will send the heat from one point to the next at a very fast rate. Right? So that's what thermal conductivity is. The A represents the heat transfer in the specific area of the conductor. So basically it's the cross-sectional area of the metal that it's, or the material that the heat is being transferred through. The delta T is the difference in the temperature, right? So the difference in the temperature of the material's boundary, right? Which means that if you look at the diagram, the heat is being transferred from T2 to T1. So therefore, there's a change in temperature from T2 to T1. So delta T is the difference between T2 and T1. Right? And then dx is the change in the thickness of the material, right? Or it's a change in the distance between where the heat will be transferred. Right? So in this case, it's being transferred from D2 to D1. So that length there is the D. All right, any questions about this equation? We're all good? All right, so let's continue. Now, the other important thing is, why is there that negative in the equation? Right? Now, the delta T over dx is basically change in temperature over change in distance traveled, which sounds like finding the gradient of something, right? Because when you find gradient is a change in the y value over the change in your x value, right? So that part of the equation is known as your temperature gradient, right? And this is negative because the temperature becomes less as the distance x increases. So what this means is that if you heat a metal at one end, right, the heat actually gets less, or the temperature will get less when you go away from that heating source. So the further the heat travels, the less the temperature becomes. All right? So that's why the value is negative. All right, so the syllabus requires you guys to know two experiments that were done by two different scientists in terms of demonstrating thermal conductivity. Right? So thermal conductivity is the rate at which the rate of heat flows perpendicular through a cross-sectional area of a solid per unit temperature gradient along the direction of the heat flow. So in small words, it's basically how fast the heat will be transferred in a specific area in a change in the temperature gradient. Right? Now, thermal conductivity is a property of conducting materials, the ability of materials to conduct heat, where good conductors will have a higher value of K compared to poor conductors. Right? Now, the two experiments are the Lee's experiment and the Shears experiment. Now, these two links are gives you a broader demonstration or description of the experiments. I'm going to actually share what happens with the link when you bring it up. All right, so let's go with the Shears first. All right, so this one is the diagram of the Shears experiment. And what this is just a copper bar, right, that has two entrances. The left side, you notice there's a bigger cylinder there. That's where steam is used to input into the copper bar. And then the right side, you have two smaller cylinders, and that's where water enters and leaves, right? So in one side of the bar, you have heat being applied. In the other side, you have basically a cooler temperature, so a colder temperature being applied to those two sides. So question is, what do you expect will happen when you have heat on the left and a colder temperature on the right? In terms of thermal conductivity, thermal transfer, what will happen?
So you said the heat is at the left?
Yes, so the cylinder on the left side, that's applied heat, and on the right side where water is going in and out, that's where the cooler temperature is experienced. So what will happen?
Sir, the heat would move towards the side with the water.
All right, so heat will move from the steam section where it's of higher concentration to where it's of lower concentration where the water is on the right side. Now, in his experiment, the T1 and T2 openings, that's where you put two thermometers there, right? And his observation is that T1 would equal to T2. Now let's explain why would you think that happens? Why after a period of time, the T1 temperature will be equal to T2. You notice T1 is closer to the steam and T2 is closer to the water part. Why would both temperature readings be the same?
Sir, energy go back and forth until it becomes constant.
Great. So energy will be transferred just like diffusion or osmosis until you have an even distribution of heat throughout the copper bar. All right. So once you have a even contribution of heat in the copper bar, anywhere on the copper bar will have the same temperature, regardless of what's on the right side or what's on the left side. All right. So this proves to us that that heat actually transfers from where it's high to where it's low until it's evenly distributed. So that's what the reading of T1 and T2 will prove. That temperature will remain constant because the heat would be even throughout the copper bar. All right, so that was the Shears equation or experiment. Let's look at the other one, which is the Lee disk method. So the Lee disk method is the same, right? But this time it actually uses basically two brass discs, right? So just giving you a summary of what's happening. So he has two brass discs. Those are the gold looking ones at the bottom, and in between those two brass discs there is an insulating material, right? On the top of the disc A there is a steam chamber, so you're applying heat to the first disc, right? And hence, what do you think will happen when the steam is projected on top of the disc A? when there between this A and this B there is a insulating sample or insulating material. If you measure the temperature of this A and compare it with this B, what change, if any, will you experience? Anybody? Let's go. What change would you experience if you have the insulated material between both discs?
Sir,
Sir,
would it
there is a
prevent the heat
possibility that
from transferring?
Yes, you can
Sir,
go. The person that was.
sir, I was saying that would it prevent the heat from transferring to this too?
All right, so it will prevent the heat from transferring to this too. So in terms of temperature, what would there be a difference in temperature between both discs?
Yes, sir. The temperature in disk A would be greater than the temperature in disk B.
All right, so that shows us that if we have a material that's in between two good thermal conductors, if we have an insulator, then because of that thermal conductivity of the insulator being low, it's going to prevent the even distribution of heat between this A and this B. Now question, do you think insulating sample would prevent totally the heat, any heat from traveling from A to B?
No, sir, not completely.
Not completely. Great. So insulating materials do not block entirely the heat being transferred in it. What it does is to slow it down. Alright? So sometimes we're too, how should I say, we're too lazy to observe for a longer period of time if conductors do transfer heat. It does, but in very short period. Well, it takes a longer time for it to actually show that effect. Right? So if you continuously heat a insulator, it will actually transfer heat, but in a very slow rate. Right? So that's why it has low thermal conductivity. So that is what the Lee's experiment actually proves to us. All right, so you should be able to give a little sketch of these two experiments and actually give an explanation of what's happening. Alright, so should remember those. You will be provided with the link for both experiments so you can have it on your side as well. Alright, let's get back to the Alright, so we're going to actually go through up and down. Not going to be confusing though. All right, so we're still looking at gases. All right, and this equation should be popular. The red one should be popular from CSET days, where PV is equal to nRT, right, which gives us the general gas equation, where P represents the pressure of the gas, V is the volume that the gas has, N is the number of moles, R is the gas constant, which is 8.31, and temperature is the T. Right? And now there is a new one that you can use, which is PV is equal to NKT. Alright, where N is, you notice, is a capital N this time, not a common N. So the capital N tells us it's the number of particles of the gas. The small n is the number of moles, capital N, number of particles of the gas. The K here is a Boltzmann constant, which is 1.38 times 10 to the negative 23. And the T, the last K there should be T. The T is for temperature, that is measured in Kelvin. Is that a question? change the slide. Okay. All right. So it's important to know the difference in both equations, right? That N, common N in nRT is the number of moles, capital N in nKT is the number of particles of the gas. All right. Anybody, I probably would have students who would do chemistry. What is the relationship between moles and the number of particles of a gas? Anyone? What's the relationship that is there? Let's put it in a different term. If you have mole, the mole of the gas, how can you find the number of particles that the gas have?
You can equate it to 1 mole equals 6.02 times 10 to the 23 particles.
Great. Alright, so we just equate it to Avogadro's number. Alright, where Avogadro's number tells us that 1 mole of any gas is equivalent to 1.602 times 10 to the 23 particles. Right, so any mole that you have, all you're doing is to multiply by Avogadro's number to give you the number of particles that exist. All right, and then you should know this one. This one is called the what's this equation called in terms of gases? All right. Barnes is saying she's not seeing. Everyone seeing the slide?
Yes, sir, right now. Since it changed it. Is that the general formula of the gases? I don't know.
Alright, so Barnes, great. It's the combined gas law. Alright, so remember we have 3 gas laws. Alright, anybody remember the 3? We have
Charles' law, Boyle's law.
Charles' law, Boyle's law, and the third one is pressure law. Thank you. Alright, so 3 gas laws. So let's go and just give a revision on all 3. Let's start with Boyle's law. Who want to start by Boyle's law?
Submarine. Constant.
Which one is constant? Temperature. Alright, so what I normally use for students to remember Boyle's law is that Boyle's law is similar to the word boil, right? And when something is boiling, then the temperature of the substance is constant. So hence we use Boyle's law. The constant there is temperature. So if temperature is constant, then we're looking at the relationship between pressure and volume. So therefore, Boyle's law states that at constant temperature of a fixed mass of gas, then if the volume increase, then the pressure will decrease. All right, so that is Boyle's law. Now Charles' law, which one is constant? Yes, Charles' law. Pressure. All right, pressure is constant in Charles. So now Charles says that pressure is constant for a fixed mass of gas. Then if the temperature increase, then the volume will If temperature increase, the volume
Increase.
will increase as well. Great. Alright, so that's 2 out of the 3. The last one is the pressure law. And hence the only one that remains to be constant is the
Volume.
volume. So for pressure law, if volume is kept constant for a fixed mass of gas, then if the temperature increase, then the pressure
Increase as well.
will increase as well. Alright, so it's very easy to remember the gas laws. Right, because as I said, Boyle's law, anything that's boiling, the temperature remains constant. So temperature is constant for Boyle's law. For pressure law, it's easy to know because it's talking about pressure, so hence pressure cannot be constant. Right, so therefore volume has to be constant for pressure law. And then Charles' law would remain that pressure is constant. Alright, so once you can remember Boyle's and pressure law, then you will remember Charles' law as well. Alright. Now, we look at the assumption of the kinetic theory of gases. Alright, this is something that you should have been introduced to from doing science, right? And it's something that keep still requires you to remember at least. Normally they will keep between 3 or 4 if they're asking you to give any of the assumptions in the kinetic theory of gases, right? So one is that gases are made up of numerous tiny particles called molecules. So every gas there is are made up of molecules. Right? The molecules of a given gas are identical. That's real gases, however, have molecules containing isotopes, and therefore not all molecules in such gases may have the same mass. That's something that we talked about at the start. Right? So in the ideal gas situation, all the molecules are identical. But in real life, you're going to have some gas molecules that have different masses because you have isotopes of the element. Right? The third one is molecules of a gas are continually moving independently of each other with random speed and random directions. So the net velocity is 0. Right? So the only thing that changes at the same temperature is the direction. So they have the same value of the velocity, but the direction changes. Alright, so opposing direction, that means your net velocity is 0. Alright, molecules have negligible volume. At high pressure, the molecules are close together. Alright, and then the last one is molecules are far apart from each other and therefore do not attract each other. So gas molecules in the kinetic theory of gases states that there is no attraction between the molecules. All right, you hear me now?
Yes.
So Maxine, how or why is there pressure exerted by gases? Where did this pressure came from? Who wants to go? Nobody? Nobody? All right, let's use math to tell us where the pressure came from. All right, so let's look at pressure. What's the equation to find pressure?
Force over area.
Pressure is equal to force over area. All right. Now, you learned an equation when you did momentum, which was for impulse, involving F times T is equal to mass times change in velocity. Impulse equation. Right? So hence, if we make F the subject here, we get m times change in velocity over t, and we substitute it here, which is m times change in velocity over at. Right? So we see that the pressure of any moving object is dependent on this part. So once you have a change in velocity, then you're going to have a pressure. So when you have a container with gas particles, right, these gas particles, if they move to the left, these two move to the left, right, when they hit the walls of the container, what's going to happen? Yes, no.
They're going to rebound.
They're going to rebound, right? So they rebound not necessarily opposite to where they're coming from, right? But they rebound in any direction, right? So because of that rebounding, then you have a change in velocity. So if this was v1, then this velocity that rebounds with would be v2. So because you have a change in velocity, then you have a pressure that the gas exerts on the wall. So the only way gases can have pressure is if the particles are touching the container walls. Right? So gases that are moving in the center that don't reach the container walls as yet, those don't exert pressure. Right? They have to be touching the container walls in order for them to actually have a pressure in terms of gas pressure. All right, so everybody understands that? Where gas pressures come in? Yes?
Yes, sir.
All right. All right. So these are some terms also that we need to know about gases. Should know about the root mean square speed of gases, which is noted by that bracket C and the square. Right? This is the measure of a speed of a particles of in a gas. So it's basically is the average speed of particles or the molecules in a gas. Right? Now these are some equations that we're going to use, or that you should remember. That n, that common n means what again?
Number of particles.
The number of moles, not particles, common n. Right? So common n is the number of moles, right, which is equal to m over capital M. This should be familiar to chemistry students. So the common n means it's the mass of the gas, and the capital M is the molar mass of the gas. And the molar mass is just looking at the periodic table, what's the mass of the element that makes up the gas times the amount of that element in the gas. Example? Yes, I do think the recording will be sent to you guys. All right. Now, for example, oxygen gas, which is O2, right? If you look at the periodic table, O oxygen has a mass of 14. No, sorry, 16. Right? So oxygen has a mass of 16, but because it's O2, then it's 2 oxygen, so multiply 16 by 2, and we get the mass, the molar mass of oxygen gas, which is 32. Right? So the small m is the mass of the gas that you measure with a balance. The big M is the molar mass, depending on how much element is there and the mass that is on the periodic table. All right. Then the second equation can find the same mole by dividing capital N by Na. And we know capital N now is the number of molecules of the gas, and Na is Avogadro's number. All right, so if we divide the number of particles or the number of molecules of the gas over Avogadro's number, we also can get the number of moles of the gas. All right. Now also the relationship, this relationship is important because sometimes they ask you to write the relationship between K and R. Right? And remember, K is Boltzmann constant and R is the gas constant. So the relationship between K and R is that K is equal to R over Na, and Na is Avogadro's number. All right, so that's good to jot down that the relationship between K, which is Boltzmann constant, and R, which is the gas constant, is that K is equal to R over Na. All right. Now the other equations would be the middle one there. PV is equal to 1 over 3 Nm bracket C squared. All right. The M there is the mass of the gas, and we know C in the bracket means the root mean squared value, and also P is equal to 1 over 3 rho C squared, and the rho there is density, not pressure. So the first one is pressure equals to 1 over 3 density of the gas times the root mean square value of the particles in the gas. The two last equations find us the kinetic energy, which we're going to look at how do we get those equations, because it's important to know how to derive those equations. All right, so any questions thus far? All
No,
right, okay. All right, so this is a starting of deriving the kinetic energy of gases. So the first line tells us that, remember we said that individual gas particles in a container will have different kinetic energy. All right, so we can safely say that the total kinetic energy is the sum of the individual particles energy, kinetic energy. All right, so that's where we have half mv squared, 1/2 mv squared, 2, and it continues to half mvn, which is just the number of particles there. All right. Now, the common thing here is that the mass is the constant. So we can take half mass out, and then all we're left back with is just adding the individual velocity squares together. All right. Sorry. Now, half m times the number of molecules. All right. So all we're doing is just adding the number of molecules present in the equation, and then we go to this part. All right, so we now have half m n, which is the number of particles, times the root mean square. Because remember I said the root mean square value is the sum or the average of your individual gas particles velocity, right? So you're averaging out the amount of gases, the velocities for each. So therefore it's just the velocity of each particle divided by the amount of particles there. And n is the number of particles present in the container, right? But we now will combine the PV is equal to NKT with PV equals, right? So now we have 1 over 3 Nm root mean squared value equals to NKT, right? Sorry. Now the NK, because the EK is also PV. So kinetic energy is also P times V, the pressure times the volume. So instead of writing EK, we can just write NKT. All right. So in this case, we just cross multiply, and hence we get that EK is 3 over 2 NR over NAT. And we know that K is equal to R over NA, so we can replace the R over NA with K. And also we can get the nRT from that as well. All right, so this will be shared with you so you can go through. I think this one is a little bit more challenging for some persons to understand. So there is also a link to a YouTube one that gives you a little shorter version of the derivation of these two equations. All right, so when you have the time, you can actually look through. All right, so now we look at the term thermodynamics. All right, so thermo deals with heat, dynamics deals with movement. So basically, it's how heat moves, and specifically, we're going to look at heat within gases. So these are terms that you need to know what the Q represents, what the W represents, and what the U represents. So the U is basically the internal energy of the gas. The Q is the heat that is added to the gas, and the W is the work done on the system or by the system. Now, what I mean when I say on the system is, let's look at, let's give you an example, is pumping a ball, right? Now, pumping a ball is you doing work on the ball to get the volume up or bigger, right? So that is work being done on the system. Everybody get that?
Yes, sir.
All right. So if it's now work done by the system itself, then instead of adding the heat energy and the work, we minus to get the total internal energy. So to always know if it's work done on or by the system, if it's work done on the system, in most cases, in terms of gases, the volume of the gas gets smaller. If it's work done by the system, then the volume of the gas gets bigger. All right, we're going to look at some examples using some graphs to know that. And then we look at two new terms that you need to know to define, which is your molar heat capacity at constant volume, CV, and the molar heat capacity at constant pressure, which is CP. All right, so CV, when the volume is constant, of a gas is the quantity of thermal energy required to change the temperature of 1 mole of a gas by 1 Kelvin without a change in its volume. So that sounds just like what specific heat capacity is, right? But because this is at constant volume, then it's just the volume being constant, and it's the amount of heat required to change 1 mole of a gas by just 1 Kelvin when the volume is constant. And then Cp is when the pressure is constant. It's the amount of heat required to raise the temperature of 1 mole by 1 Kelvin. So everybody understand the difference between the Cv and the Cp? Yes? Come on, guys. All right. All right, so these are equations. We went through the first 3, all right? So the other 4 now involves using Cv or Cp. All right, so delta Q, remember Q represents the heat that is added to the system. All right, so if you're heating a beaker with water, it's the amount of heat that the beaker will get. So that's Q. N, that common N, remember that represents mole. Cv is the molar heat capacity at constant volume. And delta T is our change in the temperature. All right, and then it's just the same for Cp, same equation. All right, and then Cv also, in terms of R, we can find Cv by 3/2 times R, or Cp is 5/2 times R. And R we know is our gas constant, which is 8.31. All right, so these equations are important to always remember, all right, because we're going to use them in our tutorial session. Now, another thing that CAPE normally asks is to why Cp is always greater than Cv. All right, so we know that Cv is 3/2 R and Cp is 5/2 R. So we substitute the value of R in both. We get at Cv it is 12.5 and at Cp it's 20.8. So why do you think at constant pressure it takes more energy to change the temperature of the gas than when it's at constant volume? Let's go. Who wants to attempt that? All right, so the question is, why does the Cp value, which means the amount of heat required to change the mole of gas by 1 Kelvin at constant pressure, why is that value greater than the Cv when the volume is constant?
Sir, is it because the coefficient of R is greater than the coefficient of R in the constant pressure is greater than the coefficient of R in the constant volume?
All right, so why do you think the coefficient is different? Nobody? All right, let's ignore what's on the screen. Let's just talk about gases. When you apply heat to, let's go with standard volume. So we can't change the volume of the gas, just like your cylinder. So your cooking cylinder, if you apply heat to it, right, it's basically saying, why does this one change temperature faster than if it was applying heat to, let's say, a plastic container that will expand when you apply heat to it. What's the difference between the cylinder and something that will expand? What's the main difference between those two containers?
The volume for the expanding one can change, but the cylinder will be constant.
Exactly. So if you have something that will always be the same volume, then the heat that is required only has one job to do, right? Which is just change the temperature of the gas. So that's why CV is small, because all the heat that is sent to it, it only goes to just doing one work, which is to change the temperature. But if you take, for example, a container now that when you apply heat to it, it's going to change volume first, right? Because that's the first thing that any object that can change volume will do. Once you apply heat to it, it's going to change the volume first, and then it's going to use some of that energy to actually change the temperature. So therefore, you need an excess amount of energy to change the volume first before it can change the temperature. So that's why CP has a greater value than CV. All right, so always remember, so CP greater because the energy, initial energy sent to it is to change the volume first, and then the additional is to change the temperature. While CV, because the volume is constant, the only thing that the energy that will be supplied to it will do is to change the temperature. So it's going to be a lesser amount needed to do that. All right, now these are what we call our PV graphs. PV because it's just showing the relationship between pressure and volume of gases under different conditions. All right, now a thing to note about these graphs is that to find the work done to do this curve or this line is to find the area under the graph. All right, so to find the work done is just the area under the graph. All right, but we're going to look specifically at what these graphs tell us. All right, so let's look at the graph on the left. So the graph on the left tells us that once the volume increases, then the pressure is reduced or decreased. All right. Now, in this case, because of the shape of these curves, it's an isothermal process. An isothermal process means that the temperature of these gases do not change. So the temperature does not change, but the volume increase and the pressure is decreased. Right? So if your examination, if you see a curve that looks like this, and asks what process is taking place, then it's an isothermal process. So iso means same, thermal means temperature. So it's the same temperature that the particles will have when the volume is increasing and the pressure is reducing. All right, and then the one on the right, the tells us that the black line, the black curve there, is a adiabatic process. Right? Now you notice the difference between both is that the one on the left, both lines will never meet because the temperatures are constant. So whatever temperature B has is different from whatever temperature A has. But in this case, the red line and the C line, they have the red line will never change temperature, so it's isothermal, but the black line is an adiabatic process. An adiabatic process is basically, it does not release heat to the environment or it doesn't take heat from the environment. But inside the container, the temperature can change. Right? So it's just basically you're in a room that the heat that is in the room will never leave the room. Heat from outside will never enter inside, but the temperature inside the room can fluctuate. Right? So you can have this temperature now, and then it changes just a little after. Right? So it fluctuates the temperature, but the heat, the total heat is always the same inside because it doesn't change heat from inside to outside or from outside to inside. Right? So we learn about the isothermal process, the adiabatic process, right? And then the next one is called the isobaric process. And if you notice, we're just focusing on the blue line where volume moves from 2 to 5, right? But the pressure of the gas remains at 200 kilopascals. So in this case, volume change, but pressure does not change. So remember, iso means same, baric means pressure. So isobaric means same pressure. So you're changing the volume, but the pressure remains constant. All right. Now, question, why would the pressure remain constant even if you're changing the volume? Because remember, changing volume means that your pressure should, if you're increasing volume, then that means the molecules now have to take a longer time to reach the container walls to get the pressure. So the pressure should reduce. Why is the pressure the same, even when the volume is increasing? Anybody wants to take that on? Why is the pressure the constant? What could cause the pressure to be constant when the volume is increasing? Nobody? Why so like everybody going to sleep? All right, somebody gives the answer. So Kyle Anthony, the temperature. Great. All right. So the temperature has to change in order for the pressure to remain the same. So when you increase the volume, you also would have to increase the temperature. So that means the gases get more energy so they can reach the container walls even when the volume becomes big. All right. So the increase in temperature will cause this to occur, the isobaric process. All right. Now, there's also another process, which I'm not sure why it's not here. It's called the isovolumetric process. And by that term, you should know what it means. Isovolumetric. What would be constant there?
Volume.
The volume. And in that case, it would look like, if we look at this one here, the side that is CD or AB, those are isovolumetric. Because you notice that those two processes in the cycle, the volume remains the same. So at AB, the volume will, from A to B, the volume is same 2, and from C to D, the volume is still just 6. All right, so the volume does not change, but the pressure changes. And again, that's caused because of the temperature changing. All right, now in that case, there's something special about the work that is done. So in AB and CD, there is no work done. So the work done in isovolumetric processes is always 0. All right, so that's something to remember. Work done in isovolumetric processes, always 0. The reason for that is because remember we said to find the work done is the volume under the graph. There is no under the graph in those lines. All right, so therefore the work is 0. Or you can use the equation work is equal to power times change in volume. Pressure times change in volume, sorry. So we have the pressure, but there is no change in volume. So when there is no change in volume, then there is no work done. All right, so that's something to always remember. We're coming down. Good. Now, before we go to the thermometers, the work done can be negative and it can be positive work that is done. Why do you think work can be positive or the work can be negative? What would cause the work to be positive or what would cause it to be negative? Anybody? What causes the work to be positive or what causes it to be negative? Pressure is increasing or decreasing? No, not the pressure. So remember work is pressure times change in volume. All right. So if it's a positive work, then that means we have an increase in volume. If we have a negative work, then that means we have a decrease in volume. All right. An increase in volume would mean that work is done by or on the system. Which one? Positive work. Is it work done on the system or by the system?
On the system.
On. Mm, done. So when it's positive,
On.
work is done by the system. And when it's negative, we're reducing, so work is done on the system. So let's explain again. All right, let's use a balloon. Work is done on the system, by the system, meaning let me see that. Oh, sorry about that, Barnes. That example was not a good one for that case. I was just using that one for the change in the volume aspect, but not for the work done on or by the system. But for work done by the system means that the gases are now expanding, right? And then on the system mean that something have to be pushing down on the gases to make them come smaller, so the volume gets smaller. All right. So when it's talking about the system that we're looking at is the gases. What's happening to the gases? So if we have an increase in volume, then that means the gases get energy and they're pushing on the containers to get more space. Right? So the by system is the gas pushing on the containers. On the system now is the container pushing on the system, which is the gas particles, to get them closer together. So hence the volume decreases. So positive work is work done by the system. Negative work is work done on the system. All right, clears that that clears it up now.
Yes, sir.
All right. So please make a jotting of that because it's important. Because when you calculate the work done by gases, you have to note if it's positive. Well, if it's positive, you just write the positive number. But importantly, if it's a negative work done, you have to put the negative in the answer given. All right, and you'll know if it's negative if the volume decreases. If it starts at a higher volume and then goes to a lower volume, then we know that it's a negative work, and hence you have a negative answer. All right, so let's get back to this part now, which just tells us about the different thermometers. All right, so I think we soon finish. The last thing is about thermometers, which most of it is just reading and stating why we need this one to use at different cases. All right, so liquid in a glass thermometer is the first one that is required to know. So the liquid in the glass could be mercury in glass or alcohol in glass. So the mercury is the one that you use in your labs. All right, so these they have two fixed points, which is your ice point and your boiling point. All right, so your ice point is where you're melting or freezing point, and your boiling point is 100. So all our lab thermometers that you use are just like that. It has 0 as a reference and 100 as a reference. All right, so you look at the advantage and disadvantage between the alcohol one and the mercury one. So let's go with advantages for the mercury. So it's cheap. That's why we use them in your school labs. They're cheaper than normal. They're durable. So unless the student drops it and breaks it, it works for a very long while. All right. It's easily calibrated. Calibrated means that if by any chance the markings, your scales on your thermometers starts to rub off and you can't see them, we can easily recalibrate it in the lab without buying new ones. Right? It does not stick to glass. So when you have it in your beaker, it will not stick to the beaker and hence give you an inaccurate reading. Right? So it's not an attractive material. Disadvantage, it displays is harder to read. It's slow, it has a very slow response. So literally, when you use the mercury thermometers, they actually don't give you accurate readings if you need a sudden change in temperature. Right? So let's say you want to record a temperature change every 5 seconds. Your mercury thermometer is not a good one to use because the mercury thermometer takes a while to adjust its level of the mercury in response to the change in the temperature. All right, so that's why when you're doing experiments, they normally to read the temperature, they normally tell you to ensure that it's in the substance for a period, so it gets accustomed to the reading. All right, so any sudden changes, it's not going to pick that up at that same point where the temperature changed suddenly. All right, the mercury vapor is poisonous. So that's why if it's broken, then you're not required to actually take it up or clean up the area without a supervisor of the lab tech or the teacher present. All right, because once it gets to your skin, it can cause poison. All right, for the alcohol one, advantage, it expands about 6 times that of mercury. It's a low freezing point, right? Sorry, it's cheap and it's safe. So unlike mercury that can poison you, alcohol will not do anything to you unless you drink it, which would be very bad if you drink something that's in the lab. All right, disadvantage of the alcohol, it does not respond quickly with temperature, just like the mercury. It's a low boiling point. So low boiling point means that alcohol boils at 70 to 80 degrees Celsius. So any temperature above that, then it's going to start turning into vapors inside your mercury, inside your tube, sorry. All right, so that's the reason why the alcohol, we don't use the alcohol once in the lab, because we use temperatures above 70 and 80 all the time. So once that temperature reach that and you put it inside the substance, it's going to just start turning vapors. Right? And these will actually stick to glass. So you put it in a beaker, it can actually stick to the walls of the beaker, and hence will give you an inaccurate reading. All right, so you should know all thermometers, the liquid in glass thermometers look like this, where you have the bulb, which is the little circular container at the bottom that has most of your liquid, the mercury or the alcohol. You have your reference point, which is the lowest point on the reading scale for it. All right, and you have a column that allows the liquid to go up or down depending on the temperature. And you have your scale, which is the markings for your readings. All right, now this is something new, which tells us about the equation. Right? So in liquid in glass thermometers, we use this equation to find the temperature. Now this is a method. So this equation is used to calibrate thermometers accurately. Right? So we can calibrate it in different methods. This one is the best one to use. So the temperature is equal to, let me get this bigger so you can see it. Are you guys still seeing it now? Yes?
Yes, sir.
Okay. So the T there represents the temperature, the L theta minus L0. So L theta is the length of your liquid in the tube at that specific temperature that you need. Right? So let's say there is no markings on your thermometer. You just measure the length that it is at now. That's your L theta. And you minus L0 from it, which is L0 is the distance from the bulb to where 0 would be on your thermometer. Right? And then L100 is the length from where the bulb is to where 100 degrees will be. Right? And then we multiply it by 100 degrees Celsius, and that will give us the temperature at that specific length that the liquid is in. Is that, sorry. All right, we also have the resistance thermometers. All right, so it uses resistance to actually give you the value of your temperature. The advantage of these is that the sensor can be easily installed and replaced. It's good measurement, it has good accuracy, because temperature varies with resistance. Very, very good. Right, so the accuracy of these thermometers are very good. They have fast response and good productive. So they have fast response, meaning if there's a sudden change in temperature, then it picks up that sudden change very fast. Right? So resistance to corrosion, chemicals, and oxidation, so it doesn't get corrosive or oxidized very quickly. It has a wide range in temperature reading, so it can read from as low as a negative 180 degrees to a maximum of 760 degrees Celsius. So you notice that we will not use these in our labs because we only focus on temperatures between 0 and 100. Right? So we will not use our resistance thermometer in our labs because the range is not what we require. But if you're using for a more precise, like when you use universities or personal labs, then you use these because they have a larger range in which they can read temperatures through. All right, some disadvantage, they're expensive. Right, the fact that they can read that amount of range in temperature, definitely expensive. The large bulb size compared to thermocouple, they have the bulb part of it is very large. So this is not a very small thermometer. It requires a separating bridge circuit system. So it needs an external bridge circuit in order for it to work. It needs power, the external power source. Right? And it's self-heating caused by current flow, which can affect the accuracy of the instrument. So what this means is that if you're using it for a long period of time, then because of the heat that it produces, it will cause accuracy, a problem with the accuracy in terms of the measurement. Right? So these resistance thermometers are only for to be used at short period of time. When you're finished, you turn them off, so it doesn't actually, the heat does not affect the correct temperature that it should give. All right. You have the what is called the liquid in the glass thermometer, which is looks like that, where we just have a gas in a beaker and a liquid in a tube. So based on the temperature that the gas experiences, it will push the pressure onto the liquid, and the liquid volume, the liquid height will change in that tube. Right? So your liquid volume will change in the tube, and hence the difference in the height will be used to find the temperature change that occurred. So this is solely dependent on the pressure that the gas will exert onto the liquid to change the height. Now, a very precise one that's not used in the lab is a thermocouple. Sorry. All right, so electrons flow in the wire due to different temperatures in the two alloys. As the temperature change, current flows. Voltage is measured between the two alloys. This voltage is used to calculate the unknown temperature. So the thermocouple is very accurate way of measuring temperature because it uses current to record the voltage difference between two wires in the thermocouple. All right, because of, so remember, temperature affects current, right? So therefore, because current, the temperature will affect the current, you'll have a change in the voltage in the two wires, and hence we can use that to calculate or to present the temperature reading that is there. All right, so the final thing that we're going to look at is the, should we go back? It's called thermal radiation. Thermal heat, so basically heat radiation. So heat can be transferred from one body to another by electromagnetic waves, right? So that's the only way heat is transferred from one object to another. by the means of electromagnetic waves. This is a type of transfer which is called thermal radiation. So remember, you have three types in which heat is transferred: radiation, convection, and conduction. So we're looking just at the radiation one. So a black body is a body that absorbs all thermal radiation incident on it. So anytime you hear in physics about black bodies, these are just objects that any amount of heat that is projected onto it, it absorbs all of that heat. Right? So the intensity of the radiation given off by a given surface of a body to that given off by a blackened surface of the same body at the same temperature is called emissivity. Right? So emissivity is basically the ratio of the intensity of light that is incident onto an object as comparison to if the object was a black body, which it would absorb all of that. What is the ratio between those two? Right? The power P of the radiation emitted by a black body was studied by Stefan and derived the equation that we're going to look at. So the Stefan's equation talks about the power that black body objects radiate energy, heat with. So P is equal to E psi A T to the fourth minus TC to the fourth. Now E is the emissivity of the object. So if it's a black body, so a blackened object, then the value of E is 1 always. If it's not a black body, then the question will provide you with that value. Right? But if it's a black body, it will not tell you that E is 1. You would have to know that E will always be 1 for a black body. Right? Psi is for Stefan's constant, which is normally given in the question, 5.67, 10 to the negative 8. The T is the temperature of the radiator, the temperature of the object that will be releasing heat. Right? So the first T there is the temperature of the object that is going to release the heat or absorb heat, right? And then Tc is the temperature of the surrounding, the environment. So example, if you're going to put a cake inside an oven, so before the cake the cake is in the oven, let's say it's at 30 degrees Celsius. And then the oven, you set the oven, say at 120 degrees Celsius. So T is the cake, which is 30, and Tc would be the environment that is going in, which is the 120 oven. All right, and you notice you put those values to the fourth power. All right, so it's always important to put the values to the fourth power. And also another thing to note is that the temperature should always be in Kelvin. All right, so always convert your temperature values to Kelvin. And how do we change from degrees Celsius to Kelvin?
Plus 273.
Plus 273. All right. Now we look at specific heat capacity using the electrical method. So how we can find object specific heat capacity by using electricity. All right. All we do is to connect a circuit to the object that you need to measure the specific heat capacity to. For you turn on your switch, right? And that current that flows will cause a temperature change to happen. Right? So the energy that is supplied by the electricity is your power times the time it takes. All right? So if you're recording the current flow for, let's say, 10 minutes, then the time is 10. The power that you use for your battery or your power supply is P, all right? And then that's equal to MC delta T. Right? So you would have measured the mass of the object that you want to find the C for, and then you measure the temperature change. So before the experiment, what was the temperature? After the 10 minutes, what's the temperature? All right? And that gives you the basic, the method for measuring your thermometer, your specific heat capacity, sorry. All right, and then the final thing is greenhouse effect. All right, so question, who wants to tell me in brief, let's like in 30 seconds, how does, how, how is the greenhouse effect started, or how is it generated? What causes greenhouse effect? Yes, who wants to go? What causes greenhouse effect?
Gases such as carbon dioxide.
So gases such as carbon dioxide. So what does, all right, so we have those gases in the atmosphere,
Heat
yes,
that
but
get
what do
trapped
they
in
do?
the
So they keep heat trapped. All right, so yes, so when the radiation from your sun is enters Earth atmosphere, these gases will actually absorb those radiation, all right, and hence they will now have more heat or radiation in them, so it will cause the atmosphere to get hotter than it was before. All right, so that's a simple definition of what greenhouse effect is. So without those gases, then that means you will not have that heat that is absorbed. Right? So if you don't have those gases, then Earth will not be heated by the sun, which is bad. But if you have too much, then it's heated too much, and hence you get the greenhouse effect, right? So that means you have to have the the optimum amount of these greenhouse gases in order for Earth to be heated at the right amount of radiation without it being getting too cold or too hot. All right, and that's where we're going to actually stop. That's it for thermal physics, what is required from CAPE. I hope you guys got something, learned something, or just get it cemented in your memory of what is required. So I think our